Hi, I'm Dan Zuckerman from OHSU in Portland, Oregon. What you're about to see is a set of narrated slides on some of our recent work. I hope you'll find it helpful, and I just wanted to say hi up front by video and also offer to address any questions or comments or concerns you may have with the material in the slides. Feel free to reach out. Some of the material is a little bit advanced, but I hope you'll find it helpful. Okay, here are the slides. Hi, I'm going to talk about some recent advances we've been working on for weighted ensemble methodology. This talk is not geared toward true beginners who haven't done any weighted ensemble, but people with some familiarity with the approach and from beginners to experienced. I'll talk a little bit about some of the challenges and limitations in weighted ensemble, namely correlations and variance and statistical error. And then our approaches to trying to overcome these limitations using post-analysis on the one hand, and on the other, some work that's a little bit more in progress on improved binning strategies. So let me just remind you, if you haven't thought about it, why correlations are so prevalent in weighted ensemble. And in a way, it's kind of obvious if we've started down here in the lower right, doing our splitting and so forth. If you think about, the trajectories, like let's say these three trajectories out here in this box, well, all three of them were exactly the same trajectory right until that split. Okay, so that's about as correlated as you can be. And so because of those correlations, it's more difficult to judge the statistical quality of a weighted ensemble simulation. That has a direct manifestation in the variance. So let me just try to give you a hand-waving example. Let's say that you're studying the system with two states, but there's also two pathways to go from A to B. So you can imagine, depending on how you've binned up this space, it could be that, and just any other aspects of your weighted ensemble simulation, it could be in a given run that you only sample a given pathway. Okay, so that would be sort of be the worst outcome. I mean, other than seeing no pathway. So in going from A to B, let's say you just do some runs where you only see the top pathway, and other runs, so I'm talking about totally separate independent runs where you only see the other pathway. And so that's because, the trajectories are correlated, so if you get your first successes here, this is where they're gonna go, right? So if you have some runs that see only one pathway and some that see the other, that's how you get variance, right? Because you're going to get different results depending on which way you go. So that's intrinsic to weighted ensemble. There's often some kind of correlation, compromise you have to make in any of these advanced methods. It's not always obvious what it is. In weighted ensemble, it is, at least by now, fairly obvious to us. So another question that I want to talk about is how to analyze transient data. What I'm showing you here is multiple data from multiple weighted ensemble runs showing the flux into a target state. It happens to be a protein folding simulation, but you can just see this wide range of values. These light gray lines are individual runs, and a few of them are just highlighted in colors. So that's a lot of variance, orders of magnitude, and we want to reduce that variance. So we'll be talking about some solutions for that. All right, to put us in a position to understand at least the basics of the ideas that are going to be put in practice to address those problems, let's just go through some of the theory, some of the most important aspects, and I'll be giving some references where more of the details can be found. So one of the things that you'll hear me talking about a lot is the steady state. So the steady state is really a very important part of analyzing kinetics and mechanisms and systems, and this is just a schematic. So we imagine basically that we're initiating trajectories in A according to some distribution there, and they're making their way over to B, and when they reach B, we feed them back to A according to that distribution. And we do that for a long time until they reach a steady state, in the sense that it's a constant amount of probability entering B per unit time, and indeed a constant amount of probability kind of flowing through any surface you would use to cut this space in different parts. So one of the most important quantities you get from the steady state is the first passage time. The first passage time is given exactly, or the inverse of the first passage time is given exactly by the probability flowing into B per second. So if you sit in state B and just count the fraction of trajectories or the fraction of weight that's flowing into the state per second, that's exactly the inverse of the mean first passage time. So that's kind of a remarkable result. I have a discussion of it on my blog if you're interested. But it raises this, kind of tantalizing idea, right, that we could estimate some very long time scales, namely the first passage time, which generally is something that we can't access, otherwise we wouldn't be doing weighted ensemble in the first place. And we can do that in principle from a short simulation if somehow we can get our system into steady state. So that's what we're trying to do here, or one of the things we're trying to do. Now this equation here is called the Hill relation. We're also going to see it in a slightly different form, in a discrete form, if you cut up your space into little regions. Maybe they're bins, you could call them microbins, you might call them microstates, but in any case, in this, you can cut up your system into different little states, and these red trajectories are kind of this steady state. This is just a decomposition of equilibrium that we've discussed in the past. But in any case, the usual bin-to-bin transition probabilities are given by actually a weighted sum of the two, the transition probabilities in the two directions, namely from the red ones or from the black ones. So between any two states, you would just use the red trajectories, which have started at A, to calculate this transition probability. And then in turn, this first passage time relation looks a little different, but it's really, if you look at it, this is just all the probability that's flowing from I to J, right, where I is not in B and J is in B. So it's the total probability flowing into B. And this, the nice thing about this relation, when you have these subscripts here and you're not doing a simple Markov model, is that this is valid for any states and any lag time. So that's a very powerful combination that we're going to take advantage of. So now I just want to show you some examples of applying or using the Hill relation to estimate first passage times in some protein folding studies that we published recently, or well, a year ago now. This is an example of watching the flux into the target state. So in this case, the target state would be the folded state, and the flux again is the probability per unit time. So that's being plotted here, And the rate constant is here being estimated by the inverse of the first passage time. So that's just the flux. That's what we're looking at. So initially, the flux coming into the target state is 0 at time 0, right? It takes some time for the first trajectories to reach the folded state. And then you'll see the probability increasing and then hopefully reach a steady value. Now, there's no guarantee that a simulation has to reach a steady value, but in this case, it seems to have done it quite quickly, on the order of just a nanosecond or two. And then you see these light gray lines here are individual simulations, okay? So, and those have a certain amount of variation among them. Here, it's not really that bad. These are using two-dimensional bins for this NTL9 system. And you'll notice that the experimental folding time is down here and our estimate is up there. I just want to point out that this is a low friction simulation. So you expect there to be a substantial difference, and I'll show you the high friction version in a moment. But this is just an example of using the Hill relation. So this enables you to estimate this experimental folding rate. And here, by the way, the experimental folding time is given as just a rate reciprocal, but it's still at this value. So sorry for the confusion there. So now we're doing it at a higher friction, and then you can see, as I suggested before, that the value that it reaches is not too different from the experimental value. It's still not quite the same, but again, we're doing, it's a different solvent model. It is just a model. It's not the actual system. And the force field, gives what it gives, and this is our estimate of it. But what you see here are a couple of new features, right? You see that in particular, the time it takes to relax into the steady state, what we sometimes call the relaxation time or the transient, is extremely long compared to the other case, right? Here it was just a couple of nanoseconds, right? Here it looks like it's taking about 25 nanoseconds. And then also you can see that the variance is much larger. Now this is a different setup. These are totally different runs. These are just one-dimensional bins, meaning there are fewer. Basically, that amounts to having fewer walkers in each run. And again, each gray line is a separate weighted ensemble run. Okay, so I just want you to kind of get a feel for this data. Here's some other data the same type of data for a different protein, protein G. And this is a slower folder, though this one, seemed like somehow it relaxed pretty quickly and then leveled off, even though the shape of this curve is pretty unusual. I think anyone would see that and be a little concerned. Nevertheless, this is what we found. And these red lines are a kind of a crude confidence interval, not a 95%, but more like a 50 or 60%. That's about the best you can do with this type of data. But you see a lot of variance. Again, these gray lines are individual weighted ensemble runs. So what we see here is, sort of these typical systems, is we see a lot of variance. Sometimes we see some sketchy behavior, or sometimes we see slow relaxation, sometimes we see all the above. So it's not completely satisfactory just to do what I would call a direct analysis of this weighted ensemble data. In other words, just to analyze the flux and try to use the Hill relation in order to get that rate constant, which is an inverse mean first passage time. So instead, we're going to try a little bit different pipeline, doing a post-analysis. So this is an overview of what we do. We collect regular weighted ensemble trajectories, so just like the data I showed you. In fact, that's the data I'm going to be using. And we feed it into a Markov state model tool called PyEmma. All we're using PyEmma for is to create what the Markov model community calls microstates, what we'll call microbins. And the reason they're micro bins as opposed to regular bins is they're much smaller than weighted ensemble bins, and that's important. Basically, the larger a bin is, you can imagine, even if the bin is very finely constructed in whatever coordinate you chose, there are orthogonal coordinates, and so often the relaxation will be slow in these orthogonal coordinates, and then by having smaller bins, you hope to improve basically the relaxation properties of those bins. So you want to make them kind of fast relaxing as possible. But in any case, then once we have these micro bins, right, we can go ahead and play this game. Okay, this is using the Hill relation, and you might say, well, that's just like using a Markov model. Sort of, but we're only using these directional transition probabilities, as I mentioned before. Okay, that's what this alpha superscript means. And that's what we get in weighted ensemble, right? We only get, or not only, but in this case, we're only getting the trajectories in a single direction from unfolded to folded. So it's going to directly go into this discrete Hill relation, and then we'll estimate the rate constant just in this way. So let me show you some results of that analysis, and that's by the way, when we have a lot of trajectory data, we put into PyEmma, we don't have to do any kind of lag time analysis or anything like that, because that Hill relation, as I mentioned before, let me go back to it, this is exact for any lag time. Okay, so that's quite important. So we can do it at short lag times, and we just do it at the shortest lag time that we have saved. And so what you find, this is the first system I showed you, and go in the same order as the low friction system, right, which basically folds faster than the experimental time, now shown in gold. And in other words, the rate constant is higher, so it's faster. And this is what you saw for that data. This is just the red lines from the prior plot. And this is what we get by throwing in this data into that pipeline that I just mentioned. We get this green confidence interval. And again, we know it's faster than the experimental time. It's implicit solvent, it's low friction. Of course, it's just a molecular model. It's not the true system. So that's fine. It's consistent with what appears to be the steady state of the red data. So that's in some ways like a validation or reality check. So now we're going to do the same analysis, but on the high friction data. So we take, again, all the data I showed you, and there are all those individual runs, right, with the gray lines. We feed them into this HAMSM, as we call it, history augmented Markov state model, and you get the green interval there. And you can see that that's much better aligned with the experiment, which is nice to see. Of course, again, it's just implicit solvent, but still. Now let's look at this data. This was the weird data, right? It had this very sudden sharp turn here, which didn't seem that believable, right? This had a very large variance amongst many individual runs, as you may recall. So when we look at this data, and we look at the experimental values up here, and now look at where the HAMSM is. So it's able to see from this data, even though the direct analysis shows a slower folding time with this very artificial looking shoulder here. This HAMSM analysis suggests that the true relaxation is some smoother process like this. So you may look at this data and say, well, that's a little, hard to believe. I don't know what you did there, and you got that green to overlap with the experimental. Is this something that we should believe? And, we asked ourselves the same question, even though, of course, we were biased to believe it. So what we did was we actually, notice that this data ends at 15 nanoseconds. So we're just doing the weight ensemble for 15 nanoseconds. And the red is that sort of weak confidence interval that I mentioned before. So that data that was red, unfortunately, is shown here in gray. This is the same data. This blue is the confidence interval that was there before, and this is sort of roughly the experimental value. And what we did to convince ourselves that this result wasn't a total fluke was we took these simulations and we basically used the HAMSM information to reweight the trajectories that were there and restart them in steady state. So that's an idea that's actually been around for a little while. We had proposed it back in 2010, but we never applied it before using such fine bins. So when you do that with these same gray runs and you reweight them, what you get are the red runs. Then you can play the game again. You can say, okay, well, let's take the data from the red runs and build a new HAMSM. And what do you get? Well, you get, so there's a lot of information on this slide, but basically this is with more bins. So it's actually the lowest value here, which is the best estimate. These are with finer and finer micro bins. And then you can restart it again and play the same game. Anyway, it seems like it's settled down in this region near the experimental value. It is a little faster, which is not that surprising. Again, this is actually a lower friction representation. So all that is fine. So we're quite happy with these results. All right, so now we want to move on to optimizing binning. So if you think about everything I've showed you up to this point, basically I've said, hey, our data wasn't so great. There was a lot of variance in it, and so therefore we developed these sophisticated analyses to extract better information from it. And that's what we did. But begs the question, why don't you just try to improve the simulations in the first place so the variance isn't so high, and that would save you a lot of trouble, or maybe make the performance better, and surely that would be the case if we could get lower variance. I'm sure the HAMSMs should be better, everything should be better. So the work I'm going to describe to you is a collaboration with David Aristoff, who came up with a lot of the key ideas here. And I'm going to just show you a kind of a toy model that it's just one-dimensional potential. And we're going to start here. This is like our source, and it's like our state A, and this is our sink, state B, and we'll try to calculate the first passage time there. And just ignore these. We're not actually going to use these bins. I'll show you what we're going to use. So this is the way we kind of want to do this process. So first we're going to do an initial weighted ensemble simulation with any old bins we can think of. They'll probably be evenly spaced. Then we're going to build an HAMSM like before using these micro bins, so quite fine bins, finer than we could probably afford to use in the original simulation. And then based on this HAMSM, we're going to use the formulations that David Aristoff developed to help optimize these bins. In other words, to say, hey, where should you put the bins to reduce the variance? For example, if you only have a certain number of bins that you're going to use. So let me show you some examples. And so the bins that we use in weight ensemble sometimes we'll call macro bins as opposed to these micro bins. So these are the macro bins down here, and these are the micro bins. So these are examples of the optimized bins that you find depending on how many bins you ask for. So if you want just 4 bins, they look like this. If you want 8, they tend to look like this, and so forth. So it's interesting that they tend to find the barrier tops in this system. Now note that it might be a little different potentially if the barrier were a little higher. This is not a very high barrier, but like I said, it's just a toy model. So let's look at the results. The graph on the left is just confirming that we're getting the right value for the first passage time. So all the different methods agree. In other words, it's all unbiased, as it should be, of course. That we're just changing the bins. But on the right, what you're seeing is a measure of the variance, right? So the variance is sigma squared. This is just like the standard deviation. And what you can see is that if you just so the black is just using brute force simulation. The green is regular weighted ensemble using a uniform number of bins. But as you optimize more of this process, so you can optimize both the bins and what David Aristoff calls the allocation, just the number of walkers per bin. And as you do both of those things, you can really start cranking down your variance in this system. So the blue down here is with optimal bins and allocation. And the math for this is a little complicated, but it's basically, you can make an estimate. The way the idea works, maybe I should have said something about that. Let me go back to the pipeline, is based on this sort of HAMSM, or just think of it as a Markov model for now. You can make an estimate of the variance that you'll get as you sort of join up different bins or put different numbers of walkers in bins. And that's what we do. So we use this model to make an estimate for the variance, to figure out what's going to be the optimal setup, and then we run using that setup. Now let me show you a little more interesting system that's trying to be a little more physical. So in this case, you'll see here's state A in the lower right, state B in the upper left. You'll see this is a serpentine kind of potential. Some of the barriers are, multiple KT on the order of, so let's say 6, 7, 8 KT. In some instances. And then I'm also showing here these radial bins that are like RMSD bins. You can think of it if B were like a folded state. But this is literally a two-dimensional potential, just like you're seeing here. It's a toy model. And I wanted to show you, so the procedure again is to make that HAMSM using microbins. And when you do that and you join up the bins in an optimal way, you get something like this, which is a little hard to look at first, but the more you look at it, the more it's quite interesting. So the first bin would be this light color, the next bin would be this color, and then this color, and so forth. And all those, they're surrounded by white. So what you see is that the optimal bins sort of follow this path. And in some sense, what they're like, if you're familiar with an object called the committer, which is the probability that you'll essentially proceed to the target state before the initial, they kind of follow the committer. That's qualitatively what these bins do, and that makes sense. And so it's actually able automatically to kind of see the shape of this potential, even though, of course, we're not telling it that. It's just doing simulation. And the simulation data that was used to derive these bins is based on these very naive radial bins. Okay, so we did weight ensemble with the radial bins, fed it into PyEmma, used microbins to build a new model and then combined them to generate these bins. And then if you look at the improvement in variance, and now what this data is actually showing you, systems that were restarted from steady state, I mentioned that before, you see a very significant improvement. So basically just these naive bins on the left are this gray blob. So you can see the sort of the variance that results from that, and it's kind of slow to settle down. Whereas the red ones are the adaptive, the optimal bins, and I'm going to ignore some of the details here, but these are the optimized bins, and you see the variance is much smaller, and it's super steady. So we're quite happy with this result. Of course, it's just a toy model. So what we've seen is that this approach works well in toy models, and the real question is, how does it work in molecular systems, which are the ones we really care about. We don't need weighted ensemble or any kind of optimization for these toy systems. And here's some initial data on a protein folding system. It's essentially what one of the ones I've shown you before. The system is the NTL9 in a low friction continuum solvent, but this is using one-dimensional bins. So as before, these gray lines are just the individual runs. You don't see any transient here because these were taken when the system had already reached steady state, which, as you may recall, happens very quickly. And then we also took the transient data, and we built an MSM from it, did the optimization, and built new bins, and those ran, and moreover, we started them from an estimate of the steady state. And so when we did that, we get these red curves. So it's not exactly apples to apples because they weren't started from the same exact point. The gray are just the the runs once they had reached steady state, and the red were started from steady state according to the HAMSM. So these have a much lower variance. We have to see if this holds up, but it's a very exciting result. You can see how many orders of magnitude difference this is in terms of the variance. So yeah, these are just some of the things that I said, and otherwise these runs were similar in number of walkers and number of bins, so we weren't cheating in that regard. It's just different ways to initiate the steady state. So I wanted to finish up by just mentioning a few topics that you can read more about. In particular, these items here, and one of the important ones that comes up when you have high variance, especially what we call high log variance, when those rate constants are spread over orders of magnitude, as we saw many times, or the estimates are spread over orders of magnitude. You have to be very careful analyzing that. We initially tried to do regular bootstrap, but the bootstrap has some pretty serious artifacts in this kind of regime where you have a relatively small number of estimates with a big kind of spread in log space. So we used a Bayesian approach, which you can read about. And then we also done some new analysis on probability currents, bringing to bear some mathematical concepts with some collaborators. And there's something that I didn't talk about today, but there's a flux profile, basically as it's the flux or the probability crossing a surface as a function of some coordinate. Here I'm just denoting as x, but that's something that can be used as a diagnostic and even to place upper and lower bounds on the steady current, which of course is what we want for the Hill relation. And then finally, you may wonder why these systems can relax at all if they have a sort of microsecond or millisecond folding time or first passage time, how can they possibly relax in, you know, a couple of nanoseconds or even 50 nanoseconds? Of course, sometimes they may not, but we did see some examples of fast relaxation. And there, I wanted to point out that there are theoretical reasons to expect relaxation to the non-equilibrium steady state with a source and sink, as we've been using, to be significantly faster than the relaxation to equilibrium. So I have some notes on this in my online sort of cell biophysics book, so check that out if you want. And let me give a lot of thanks to people who did this work. Most notably, Jeremy Copperman really did all the heavy lifting on the advanced analyses that you saw. He's been doing all that work. The HAMSMs were originally developed with Ernesto Suarez, and Upendra and Barmak carried out a lot of the simulations and analysis that I showed. And I want to particularly thank our collaborators, David Aristoff and Gideon Simpson, who are both mathematicians and have really helped push us and push the weighted ensemble methodology. It's been a big help. So I hope you found this helpful, and please feel free to reach out to me with any kinds of questions.